Hello. So today I will be going over a special relativity experiment and its applications. So this is for the modern physics final exam. So here we go. So first things first, I'm going to describe Einstein's second postulate. Einstein's second postulate says that the speed of light is c no matter who the observer is. So here's a little thought experiment I came up with. This isn't the experiment I'll be describing, but it's something that helps me visualize Einstein's second postulate. So on the left here, we have an observer who has two mirrors. He's going to watch a photon bounce between the two mirrors. He's going to observe it to move at the speed of light, which we would expect. And it's going to travel a distance of L up and down the mirror. And this is normal. This classically works from classical mechanics. So he's going to see it go to the speed of light, and he's going to see it go a distance of L. However, on the right side here, we have a second observer. Now this observer is going to be moving to the right while doing the same exact experiment with two mirrors and a ball or photon going up and down between those mirrors. Now this second observer is going to see the same exact thing as the first observer, where it's going up and down, just straight up and down. She's going to see it at the speed of light and going to measure a distance of L. However, the first observer is going to be watching the second observer do this experiment, and he's going to see the ball go diagonally up and down, and it's going to travel a distance greater than L, which we had measured before as a distance between the two mirrors. He's going to see a bigger distance, but he can't see a different velocity. If you would think classically, this would be going a faster speed, which makes sense. You have to go at a faster speed to go a further distance in the same amount of time. However, they don't experience the same amount of time. They experience the same velocity. So that means instead of time being the same, time is going to be changing for the two observers, and speed is going to stay constant. So if we have that the velocity is in meters per second, well, if the speeds are the same, that means that if time and distance can change, they have to change with the same ratio. So say the first observer sees the second observer's photon go a distance of 2L. That means he still sees it go the speed of light, just like both observers see it go the speed of light, but he will experience twice the amount of time because the photon traveled twice the amount of distance. And you see that here, that if, say, on the left side it's v, and the right side we have v prime for the velocity, well, they're the same velocity, but different distances. Different distances means different time if we need the same ratio of meters per second to meters prime per second prime. So that's just kind of a way to understand Einstein's second postulate. Now, an experiment done in the real world with this is the Pi Meson decay. So how this experiment was done was they shot Pi mesons close to the speed of light. In fact, 0.99975 the speed of light. And what they did with this is they used large accelerators to speed it up, and Pi mesons will decay into gamma rays, which are basically light rays, electromagnetic waves. And so it decays into these gamma rays that will shoot out at the speed of light. So if you have the Pi meson going at the speed of light and the gamma rays going at the speed of light, well, if you would think if they're shooting out at the speed of light, that the gamma rays will be moving 2 times the speed of light, if we're thinking about it in the classical sense. However, this is not the case because of Einstein's second postulate, that nothing can move faster than the speed of light. And light always travels at the speed of light, no matter who the observer is. And the results from this experiment actually proved Einstein's second postulate. So initially you had the speed of the Pi mesons going at 0.9997 times the speed of light. And then you had the speed of the gamma rays traveling at 0.9999 times the speed of light. So they're very, very close. There's not much error at all between the different speeds. In fact, the speed is within 2 times 10 to the minus 4 precision. So it's very precise. So that's the Pi Meson decay experiment and how it's related to Einstein's second postulate. Now, on this slide, we can see how relativity has changed physics. It changes how we view momentum and energy for fast-moving particles. We now have to use relativistic formulas to describe fast-moving particles. For example, electrons moving through a strong electric field, they're going very fast, so you have to use relativistic formulas to calculate their velocity, energy, and momentum. Now, I'll go through these. These are all results of special relativity of Einstein's second postulate, essentially. A lot of experiments have been done to discover all of these formulas given. Now, time dilation is what I described in my second slide here, Einstein's second postulate. Time dilation, two observers are experiencing two different times. That's what time dilation is. Length contraction is similar. It's when two observers measure different length. Now, the velocity addition formula is relativistic velocity for a given observer. So if you have two observers, you can tell one observer's velocity versus the other. Now, Doppler effect is relativistic frequency of sound and light, etc., for different observers. The Lorentz transformation is a linear transformation between observers for velocity, distance, and time. And then you have these other ones, relativistic momentum, kinetic energy, total energy, etc. Now, total energy is given by the total relativistic kinetic energy and rest mass energy, which is mc squared, the famous E equals mc squared. That's saying that even when an object is sitting still, it has the rest mass energy. So all of these were a result of special relativity and kind of started with Einstein's second postulate. Now, some modern day usage of Einstein's second postulate would be the Large Hadron Collider at CERN, where they accelerate particles close to the speed of light, and then they collide those high energy particles to observe new particles. An example of that might be the Higgs boson, which theoretically is a particle that gives mass to other particles in the Higgs field. The Higgs field is essentially a mass-given field, and the Higgs boson particle is what interacts with other particles to give them mass, theoretically. So that's essentially how Einstein's second postulate and special relativity have been used in the modern world in some of its history, in an experiment, and an example of how it works. Thank you.